So now that we've talked a bit about Java Completable Features and its structure and functionality, and we've also talked a bit about reactive programming, let's now show how we can map the features of Completable Features onto reactive programming. So here's one way to do the mapping. We talked earlier about responsiveness. One of the ways you can make your code more responsive is to avoid blocking caller code. So what does that mean? So what does it mean to block? So in a classic environment, you can block if you invoke a method, a caller invokes a method on a callee. Typically the callee will steal the thread of control of the caller, and then the caller will do its thing. When it's done, it returns the result. Then the callee can go on and do the next thing. So that's a good example of what we often call two-way, synchronous, request-response style programming. So you invoke a method, you block, you get the result back, and then you keep going. Why is this a problem? Well, blocking will underutilize cores. We already talked a bit about that when we talked about parallel streams. It will impede the inherent parallelism on the underlying platform because it's not easy to overlap currency and communication. And it also can complicate program structure depending on what you have to do to make things work well if you have lots of blocking operations, which typically involves spawning threads. So that's the problem with blocking code. How do we address this with completable features, you may ask? Well, there's various methods that are provided in the Completable Features API, including factory methods, which can start things asynchronously where the caller doesn't wait for the callee to finish. You can have so-called completion stage methods where you can essentially have the methods switched between different threads to do computations in different background threads. And then there's also what are called arbitrary arity methods, which are absolutely fascinating methods that can allow a whole gaggle of asynchronous computations to take place in the background and then provide one point of responding when things are done. And you can wait in a way that doesn't block. You can wait to be notified asynchronously or reactively when all the asynchronous computations complete. So it's really, really, really cool. Another way you can be responsive is to try as much as possible to avoid changing threads. Sometimes it makes sense to change threads, sometimes it doesn't. If you've ever been on an interstate that's crowded, you know some people love to switch lanes all the time. And sometimes that gets them there faster, sometimes it gets them there slower, sometimes it causes accidents, but it usually causes confusion and everybody's all trying to switch back and forth. And so it can become a lot more overhead and actually make things worse. So why gratuitous changing of threads is a problem is because it can incur excessive synchronization overhead, context switching overhead, memory management overhead, and cache management overhead. These are the kinds of things that can go awry if you don't have the right concurrency architecture for your code. And in fact, a very, very long time ago, I wrote a dissertation for my PhD that talks about this if you're ever interested in reading it. And it talks about some of the issues about trying to have your concurrency architecture work appropriately for the kinds of processing you're doing and how that can make a big difference in terms of performance. And that turns out to be just as true today as it was when I wrote that many years ago. The way that this works is by the completable future model can leverage the Java fork join pool, which as we've seen has got all kinds of clever things to avoid blocking. And then there's all these other various methods. There are these so-called non-async methods, which will avoid having threads change as asynchronous computations complete. And we'll see there's a bunch of different variations here that are important to be aware of. And I'll talk a lot more about that later. So these are some of the ways you can make your code more responsive. Not blocking the caller, avoid changing threads. The next topic is resilience. The next principle is resilience. And remember we talked before about how we wanted to make the program able to keep working even if there are partial failures. So in this particular case, what we're going to use are the exception methods provided by the Java Completable Features framework. And exceptions, as you may be familiar from either C++ or Java courses you may have taken, exceptions decouple error processing from normal operations. So you can have parts of code that do things when it's a sunny day and there's no cloud in the sky and everything goes your way. And then you can have other things when it's storming outside and there's a hurricane or a tornado. You have ways of handling those exceptions. And we'll see that there's a bunch of different exception methods that are provided, which we'll talk about when we get to that part of the discussion. And even though one computation may fail and one asynchronous computation may fail, we can handle that computation's failure and then either keep going or restart or return some default value or whatever we need to do. Completable features, by the way, like parallel streams, are localized to a single process on a single machine. They don't run in a cluster of machines. That's just something to keep in the back of your head. Another important theme that is valuable to map onto the underlying reactive programming principles is the concept of elastic or elasticity. And the idea here is we want asynchronous computations to be able to run scalably. They can scale up in a pool of threads atop a set of processor cores. So assuming that we've got a pool of threads like our common fork join pool, and those map to some number of underlying multiprocessor cores, then we want to be able to make it the case that as the workload goes up, we can take better and better advantage of those cores to keep the processor humming along, doing our work in parallel. And again, you're probably best off using the common fork join pool for this because it's set up to work effectively for a global scheduling point for all the different computations within a process. But if you're so inclined, you could have your own custom fork join pool or other predefined or user-defined thread pools. The main reason for having different pools and not just throwing everything into the common fork join pool would be if there are different types of computations that have to run at different priorities. So if you have, say, the high priority tasks that run at a different thread priority or thread group priority than some other lower priority tasks, it might make sense to partition those into different pools. And that way you can take advantage of the underlying operating system scheduler's support for thread priorities. Otherwise, if you don't have different thread priorities, it's probably okay to use the common fork join pool as long as you're familiar with how to use the mechanism we talked about recently regarding managed blockers. And then the fourth and final mapping of principles onto features is message-driven. So remember, message-driven just said you want to be able to do things with asynchronous message passing and loose coupling and so on. And you could use Java thread pools, which pass messages between threads in the pool internally. And of course, the Java fork join pool really takes that even one step further. And not only does it pass threads around, pass messages around, or use messages to store subtasks to be computed, but different threads can steal messages out of each other's double-ended queues or decks. So that gives you very nice support for asynchronous message passing that's inherently designed to scale up and to maximize utilization of the underlying processor cores using the work stealing model. So that's a summary of how we can map Java completable future features onto reactive programming principles. Again, we haven't gone into enough detail yet to really scratch the itch of how to program with completable futures, but that's coming here soon. And I just wanted you to see the big picture view of how these different concepts compare and contrast with each other.